Welcome back. Today we first going to discuss the difference between off-policy and on-policy reinforcement learning methods. So the Q-learning, which was covered in the previous lecture, is an off-policy reinforcement learning method. Basically, Q-learning learns the optimal policy pi star regardless of the policy used during iterations, which means that the actions taken during iterations are not necessarily optimal or do not follow the same policy being learned, right? So before we learn the policy, we do several reward-based interactions with the environment. And especially during the learning process, they are not necessarily represent the optimal policy. On the other hand, on-policy reinforcement learning methods learn the value of the policy that is being followed, which means that basically on-policy methods update their Q values based on the actions that are actually taken by the agents. So they learn from the actual moves they make, whether they are good or bad. So this may result for the on-policy methods to converge slower than the off-policy methods, as the on-policy methods basically update their action value function using the actions that are usually taken. However, on-policy methods are basically known to be more stable. So over the long run, they basically learn in a more stable fashion as compared to off-policy methods. So today we learn state, action, reward, state, action, or so-called SARSA in short algorithm, which is a popular on-policy reinforcement learning method. I will directly present you the method. The magenta steps are quite the similar steps that we follow in Q-learning, and the green steps that we have here are resulting from the SARSA algorithm, or the modified Q-learning algorithm if you wish. So in step 1, we initialize Q values as some random values or all zeros. In step 2, we take action A. Again, we follow epsilon greedy policy. So with some, for example, let's say with some epsilon probability, we take random actions. With -1 minus epsilon probability, we choose actions based on argmax of QS and A. So basically optimal. So then we apply this action A to the environment and measure S prime and the reward. S prime, think about like we apply an action to some force action to the robot. Robot moves from S to S prime, and we measure the robot's new position S prime. Then we basically take action A prime. And action A prime is also chosen, the next action is also chosen using the epsilon greedy action choosing mechanism. So with some epsilon probability, it is random. With 1 minus epsilon probability, it is chosen like the optimal action using argmax of Q S prime A prime. That's the main difference than the off-policy methods like Q-learning. Basically, we actually take the action with the agent based on this S prime and A prime. we find A prime. And then we update in step 5 the Q value for S and A using the SARSA rule. Basically, the new value of Q at particular state S and action A depends on itself with some learning rate multiplied by the reward gamma Q S prime A prime. Again, now if you compare this lecture with the previous one, we don't put dot here, we don't look at the row, but we insert the value of A prime here. So we take the action and then find its value and minus the Q, S, and A. And basically we repeat step 2 to 5 until Q values converge or until the end of all episodes. And again, one episode, we introduced the notion of episode. Basically, you are in some states, there is a terminal state, and once you converge to the terminal state, the game is over, then you need to restart the game. And finally, step 7 is identical. We extract optimal policy using this argmax argument. All right, so let's consider the same example from the previous lecture. Basically, we have a robot that is either in 1 and 2 and would like to move to the terminal state located at 3. So in this case, states are 1, 2, 3. Action is -1 or 1. This stands for left and right. So transition function that we don't know, but we need to put it in the simulation, looks like if we are at the first state and if we would like to go left, agent stays in the first state since there is no zero state. Otherwise, if we are on state 2 and agent would like to go -1 or 1, so we are at 2 minus 1, then S prime becomes 1, robot will be at the state 1. If it is +1 to agent state, it basically reaches the terminal state. In this case, it receives a reward of 5, or in this case, agent moves as well. So this is the algorithm. We initially set up the parameters, initializing the Q table as zeros. This is for recording purposes. At the end of the day, I will show you how the Q values change over episodes. Here is the reward function. Then basically we are going to have 800 episodes. We start in some random state, either 1 or 2, because reaching 3 is the goal and the game is over when we reach the state 3. We choose a random action. For a given state, we choose a random action and then we apply that action to the system, to the environment, and based on some transition function that we don't know, we are going to measure S prime as well as the reward. So this is S action reward SAR. Then basically we are applying this action again to find action prime, the next action, which is again based on epsilon greedy action selection for the next action. And for this given S prime, we find A prime. This completes SARSA or the SARSA algorithm. And then finally we use this SARSA Q update and we also, after we complete this episode, this iteration, robot moves to the next state and A becomes the next action. And other than that, this is for recording to the Q values This is for extracting the optimal policy along the lines. It should be step 7. Yeah, step 7 that I explained to you. And finally, this is for displaying the Q table and visualization of the how Q values change with respect to the episodes. Here are the results. I am only going to show you one result. I provided a code similar to the previous video. You can play with the numbers. But alpha, the learning rate is 0.1, discount factor is 0.9, and this epsilon is 0.25, meaning that 25% exploration and 75% exploitation. So Q values converge around, maybe I will say 500 to 650 episodes. This is the final Q table, which suggests that, again, these are the actions and these are the states. So for state 1, this is greater, and for state 2, this is certainly greater. So optimal policy to reach the terminal state is 1 and 1. As this being said, I would like to thank you, and we have been covering very useful reinforcement learning tools, and today our focus was a popular on policy method, so-called SARSA. So see you in the next videos.